Hello, and welcome to the lecture for Chapter 16 from Conceptual Physical Science, 6th edition. We're well into our unit on chemistry here, the chapters that cover chemistry, that is. And here we're talking about mixtures. This is kind of an oddball chapter in a sense because we spent some time defining what is chemistry, introducing the periodic table, and in the last chapter, chapter 15, we spent the whole chapter talking about molecular bonds, which was a energy and force explanation of what holds atoms together to make molecules, because chemistry is all about molecules. But here we're going to step away from molecules. We're going to zoom out a bit and look at the more macroscopic idea of mixtures. That is, mixtures of different chemicals, so different molecules. So imagine a liquid that contains multiple chemicals. They haven't bonded together, they're just near each other. And we're going to talk about how mixtures can be affected by the rules of chemistry, such as the forces that maybe pull one molecule to another or repel one molecule from another. Certainly, we'll talk about that very important bipolar water molecule, the fact that water molecule has a positive end and a negative end, and that can drive so many phenomenon. So that will certainly come up in our mixtures because often we're talking about things mixed with water, okay? Now, when we go into future content, so after this chapter, when we dive into chapters 17, 18, and 19, well, then we're really going to get back into maybe more formal chemistry. We'll zoom back into the molecules. We'll talk about what's going on there. But let's just enjoy, in this chapter, talking about mixtures. And to make sense of what this is all going to mean, let's take a look at the table of contents, okay? So most materials are mixtures, just to appreciate how important they are. Then we're going to talk about the chemist's classification of matter and where mixtures fall in there. So some definitions. Then we'll talk about what we mean by solutions, specifically, again, a definition. Then we'll lead to a physical term, which is solubility. All right, what is solubility? How do we actually quantify that? Okay, so give it a value. Then it's all about applications of mixtures. So how do soaps and detergents fit into mixtures? What role do they play? How do we soften hard water with mixtures? How do we purify water with mixtures? And how do we deal with treating wastewater like sewage with mixtures? Okay, so really this later half of the lecture of the slides is going to be all about these interesting applications. So certainly there should be some good takeaways there, and I think that content will be quite memorable, right? Because you'll be able to think about these real life applications. Okay. So let's get into the idea of a mixture and compare it to a pure substance. Okay, so a pure substance is a material consisting of only one type of element or compound. And by compound, we mean molecule, okay? So something that's composed of more than one element, all right? So you can have a pure substance that is pure because it's truly elementally pure, which would be like gold or mercury, for example, or you could have something that is pure in the sense that it's pure water because it's only H2O molecules, okay? That's a pure substance. On the other hand, a mixture is a collection of two or more pure substances. So water mixed with chlorine, so chlorinated water, would be a mixture because we've got chlorine molecules and we've got water molecules, okay? All right, and it can be separated by physical means. All right, because after all, there's no chemical bonds that hold the mixture together. All the chemical bonds we talked about, whether those were the not terribly relevant metallic bonds or the very relevant covalent bonds or ionic bonds, all those types of bonds are chemical bonds and they require chemical processes to separate them, okay? Not physical ones. Okay, so most things we think about are in fact mixtures, okay? Sugar, all right, is an example of a pure substance, I guess, a pure sugar. But once we mix sugar with water, well, now we have a mixture of sugar and water. In other words, the sugar, the pure substance of sugar, which has the molecular name of C12H22O11, it's a big molecule, right? It's one of many different types of these hydrocarbon molecules, okay? This particular type, sucrose, is this an example of a hydrocarbon molecule? By the way, we will talk a bit about hydrocarbon molecules and their importance for biology when we talk about organic chemistry. We have a chapter on organic chemistry, which is in fact our last chapter on chemistry. But I don't want to get ahead. We're still talking about mixtures here. So taking this large molecule, C12H22O11, mix it with H2O, and you've got a mixture of sugar and water, not a new chemical. all right? Because simply the water doesn't bond with the sugar, right? Instead, the water acts as a solute, right? It breaks up anything that it can. It would break up ions. In this case, it doesn't break up the sugar molecules because they are fairly well held together. But regardless, you get a mixture, okay? So then if we're thinking about the big picture here, kind of it's fun to think about where all these classifications fall in. We can think, okay, well, we got matter. All right. Now, of course, physicists kind of say, okay, well, that's it. We just stop at matter. We acknowledge that if you zoom in on an atom, you've got protons and neutrons and electrons. Okay. So that's kind of where physicists are interested in, the particles. But chemists have a different view, okay, a different classification of matter. And that, of course, involves pure and impure, which we will 99% of the time call a mixture. Okay, but a mixture is the opposite of pure, so it's impure. Okay, so mixtures include homogeneous mixtures and heterogeneous mixtures. Okay, more on that in just a second, but first let's appreciate what we should already know, because we've definitely established this back in previous chapters. It's kind of fallen under the umbrella of many chapters, but we've talked about an element versus a compound. And again, I usually call a compound a molecule, but call it what you will. Elements like gold, sulfur, nitrogen, compounds like salt, carbon dioxide, and ammonia. Notice, right, that all the compounds are combinations of different elements. They involve different atoms from the periodic table, or different elements from the periodic table. Okay, so we've established that. All right, but now mixtures, the new content. What is a homogeneous mixture? Well, a homogeneous mixture means that it is mixed evenly. All right, homogeneous means it's the same throughout. Right, you're not going to find a difference throughout. Okay, so air is a homogeneous mixture. So that means that as you travel through the air, you should find equal parts of diatomic nitrogen and diatomic oxygen. Right, it's not like all the oxygen is on one side and all the nitrogen is on the other side, because that would be heterogeneous. More on that in just a minute. Other examples of homogeneous mixtures, which are, by the way, known as solutions in this case, at least the ones we're talking about, include salt water and white gold. All right, because white gold, after all, is a mixture of elemental gold and platinum. All right, okay, but there's other things as well. There's something called suspensions, and suspensions are so called because of basically the idea that you have suspended pockets of a material within another material. Okay, so milk has water and then solid proteins. All right, those solid proteins are suspended in the water. They're like little bubbles. Right. Anytime you could think of these chunks of material floating throughout another material, in this case water, that's a suspension. Blood is another example of a suspension, water and solid proteins. The idea here is that these solid proteins, in both cases, they don't freely mix with the water. They have certain properties, chemical properties called hydrophobic. They means they repel those bipolar water molecules, and so that causes them to clump together. That's why you get a clump of many solid proteins. So, thus, you have, by definition, a suspension. We'll talk a bit more about suspensions later, but hopefully the idea makes sense. Clumps versus evenly mixed. But it's still homogeneous because it's, again, not all the solid proteins on one side. Okay, it's evenly mixed in large chunks, relatively large, throughout the water or throughout whatever is holding those chunks. Another example of suspension that doesn't involve water, well, at least not being mixed into water, is fog. Because in that case, you have the water forming the chunks, droplets, within air. Okay, and air itself being nitrogen and oxygen primarily. Okay. All right, but we do want to briefly speak about heterogeneous mixtures, and heterogeneous mixtures are exactly what I implied. You do have all of one on one side on the other. Okay, so if you dive deeper into sand and water, you're going to get into sandier and sandier portions of that water. Why? Because the sand is sinking. All right, so it's always going to be heterogeneous. There's always going to be more sand deeper down in that mixture of sand and water. Oil and water is the same way because they don't freely mix. So the oil, being less dense than water, is going to be on the top. The water is going to be underneath. Okay? So it's anything that is going to self-separate due to some physical means, such as density. Okay? All right. So pure material consists of a single element or compound, right? I think I've certainly established that. Hopefully that makes sense. Impure materials consist of two or more elements or compounds. Very good. All right. Mixtures may be heterogeneous, or homogeneous. Okay. in heterogeneous mixtures, I always make sure I say that carefully, right? It's just a tricky word. The different compounds or components, excuse me, all right, those are the different maybe elements or compounds that are within that mixture, can be seen as individual substances. Got it right? You can tell them apart, okay? In a homogeneous mixture, the composition is the same throughout. There's no difference. There's no gradient, if you know the term. You can't, again, you can't like move throughout that mixture and notice more of one than the other, such as sand and water. So you go deeper down, more sand, okay? All right, so we have examples of heterogeneous mixtures. Here's granite, all right? So in this case, we have clearly defined, sections of different minerals, all right? We also have snow in a snow globe, clearly heterogeneous, right? Because the snow settling, you can always see that there's always going to be more towards the bottom over time. Almost all of it is at the bottom, okay? Pizza is another example of a heterogeneous mixture. Kind of silly to think of it that way. We normally chemists don't concern themselves with pizza unless they're eating it, but still, strictly speaking, it is a heterogeneous mixture. Again, examples of homogeneous mixtures, air, because you can't clearly see the difference between the nitrogen and oxygen. It's the same throughout. Clear seawater, again, because in that case, yes, there's salt in the water, but that salt in the water is evenly mixed throughout the water. And white gold, again, unlike granite, in comparison, we don't see specks of the platinum inside the gold. Instead, we see that they are evenly mixed. They're the same throughout. Because homogeneous always means the same throughout, the same in every direction, okay? So in a homogeneous mixture, a solution, all the components are in the same phase. And actually, this is an important definition I didn't mention in the previous slide, because that phase really establishes that idea of having the clumps, okay? And that's what we saw in the other case. It was the solid proteins, such as in milk. Well, that was a solid in a liquid, which was water. If it was the droplets of water, that was a liquid suspended in air, which was a gas. So anytime there's different phases, that's probably the clearest definition, then we have a solution as opposed to a solute, or excuse me for a second, the term that we had was a suspension, okay? So suspension was different phases, solution was the same phase. Okay, but anyway, we're getting there. Okay, so we have a solution, all the same phase, suspension, different phases. Okay, is that clear? So like solid in liquid or liquid in gas would be a suspension. All right, so let's do a check here. Is the air in your house a homogeneous or a heterogeneous mixture? Okay, so make sure you can answer this. Which is it? All right, homogeneous because it's mixed very, very well, heterogeneous because of the dust, homogeneous because it's all at the same temperature, or heterogeneous because it consists of different types of molecules. All right, you confident about your answer? All right, it's heterogeneous because of the dust particles it contains. Okay? Yeah, I think that's the best answer. I would also expect or accept that it's mixed very well. All right, because we made a big deal that it is homogeneous. We said air, but I guess to be fair, there is a lot of dust, and that dust would definitely be heterogeneous. So you'd find more dust near the ground than higher up near the ceiling. Okay, so solutions is a homogeneous mixture consisting of ions or molecules. Okay, and remember that the solution, unlike the suspension, also is everything's in the same phase. Now, when we're talking about solutions, that implies something. So people who have studied a lot of physical sciences, that when they hear solution, they think, well, what dissolved, right? What made the solution? Because if you often pour something in the water, it dissolves. Why is that? Because water is a solvent. Okay, and the solvent is the major component of the solution. And by major, we just mean there's more of it. So, in terms of the overall mass, if you think of mixing sugar with water, you're going to get a solution, a water sugar solution, not a suspension, because everything's going to be in the same phase. And in that case, there's definitely more water, by weight than sugar by weight in that mixture. Okay. The solute in my example would be the sugar, because that's the minor component. There's less of it. The total weight of it is less. Okay. And then when it's saturated, when your solution is saturated, that means that you can add no more or it will become heterogeneous. Okay? Because at that point, there's going to be, if you imagine you pour in too much sugar into water, eventually it no longer just disappears into the water, it starts to build up at the bottom. Why is that? Because it's no longer dissolving. It's been completely saturated. Now you no longer have a homogeneous solution. Instead, you have a heterogeneous solution. Okay? Now, you also arguably would have a suspension because you have solid sugar that's no longer able to melt or dissolve. And so at that case, you actually have two phases. You have the sugar remaining a solid because you've gone past saturation. Okay? But you could also just get right up to saturation and find that perfect amount of sugar that will dissolve in the water. That would be saturated water for that particular amount, that particular quantity. Okay? So a concentration, continuing with definitions here, is a measure of the amount of solute dissolved in solution. Okay? So that is the value of concentration. How much there is of the solute that has been dissolved in your solution. Okay? And it was dissolved into what? The solvent. Okay? So concentration then is just solute over solution. Notice solvent doesn't come up here. We could rewrite this as, since the total sum of everything is solvent and solution, we could write it as solution, right? And this would usually be a volume measurement like cubic centimeters or liters, but it could be solution minus solvent over solution. And the reason for that is because solute is just solution minus solvent. See? Because the sum of solvent and solute is just solution. Okay? All right, good. I know they're very similar words, solute, solvent, and solution, but you got to be clear on which is which. Okay? So that is concentrated. All right? Concentrated here, implied by the variable size of the text, means that there's very little solute per solution. Okay? But if there's a lot, then we say it's, or if there's more solution, then we say it's dilute. Okay? All right. So actually, let me make that a little bit more clear. All right. So here, really, the idea is that there is a lot of the solute. Okay. Not very little. I was looking at the text here and said, oh, it's small, but really concentrated means that you're close to the point of being saturated. So concentrated is approaching saturation, right? Just as the word should be, you should think of it in everyday language. Concentrated means there's a lot of the solute. You're approaching saturation. On the other hand, dilute means that you got a lot of solution, which means you have a lot more solvent than solute. So there's not that much. So just a little sprinkle of sugar in your water, for example, would be dilute. Okay? All right. So concentration, a measure of the amount of solute dissolved in solution. A mole, continuing with definitions here, this is a new one, is a super large number. That's a fun way to think about it. In fact, it's this number, right? Approximately. We can continue with further accuracy, but to three numbers, it's 6.02 times 10 to the 23, which is almost a trillion. Okay, it's 100 billion trillion. Okay, because a trillion is 10 to the 12. This is almost two of those, right? So 10 to the 24 would be a trillion. Okay, so it's nearly a trillion, and it's used to measure numbers of atoms. Okay, again, atoms are so small that a trillion or almost a trillion atoms is not that much on a macroscopic scale. All right, and a mole is an Avogadro's number. That's the name of this number. In fact, that's what that's called. If you see 6.02 times 10 to the 23, you often hear people say, "Oh, that's Avogadro's number," because that's how many atoms there are in a mole. Now, this can be a tricky idea, right? So wait, you're like, wait, that's how many atoms there are in a mole, but does it depend on the element? Well, no. Every mole of an element or a compound has that many pieces, right? That many molecules or that many atoms in a mole. But not all moles are the same, therefore, because obviously if you have heavier atoms, then your mole is heavier. So a mole of gold is heavier than a mole of hydrogen, much heavier, in fact. Okay, but they both have the same number of atoms. Okay, so the formula mass of a substance expressed in grams contains 1 mole. All right, we say that's the molar mass. And again, heavier elements that are have a higher number on the periodic table, right, a higher atomic number, well, they are going to have a larger number of grams in 1 mole. Okay, so for example, carbon, which has 12 protons, because it's defined by the atomic number 12, has a molar mass of 12. Oxygen has 32. Why 32? Well, because each oxygen is 16, because the elemental number of oxygen, or the atomic number of oxygen, is 16, but there's two of them because oxygen comes in a diatomic form, pure carbon does not, and therefore the formula mass, the molar mass of oxygen would be 32. In other words, there'd be 32 grams per mole, okay? So grams per mole. All right, carbon dioxide. Well, carbon dioxide is a molecule including carbon and O2. So we'd sum up the atomic numbers of carbon and two oxygens, and that gives us 44. And you would refer to the periodic table to get those values. And again, it'd be 44 grams per mole. All right, so carbon dioxide is heavier. 1 mole of it is heavier than 1 mole of pure oxygen, diatomic oxygen. All right, and we get into sucrose. And sucrose, 1 mole of sucrose is downright heavy. It's 342 grams, about a third of a kilogram. Okay? All right. So 1 mole of sucrose equals 342 grams of sucrose, as I just said. Why? Because its atomic mass is 342. All right? Because literally that is how many protons there are in one molecule of sucrose. Okay? Really, that is absolutely the fact. That's an important one way to think about a mole, and one important way to think about a mole. Okay? And that means that there is exactly 6.02 times 10 to the 23 molecules of sucrose. Again, I'm not saying atoms, because every molecule of sucrose has quite a few atoms. In fact, it has 12 plus 22, so 34 plus 11, so it has 45 atoms per molecule. But molar mass doesn't count atoms, it counts molecules, that smallest piece. All right, and sucrose, its smallest piece is, it's C12H22O11. Okay, so that means that sucrose, as I said, is 342 grams per mole. Okay, all right, good. So water, H2O, has a formula mass of 18. Okay, that's just summing up its atomic numbers, okay, of its constituent atoms. How many moles of water are there in 18 grams of water? Make sure you can answer this confidently, because that would show yourself that you have that understanding of what a mole is. Okay, got your answer? It's 1, because 1 mole of water, after all, since it has a formula mass of 18, weighs 18 grams. Get it? All right. Okay. So how many grams of water are there in 2 moles of water? How many grams of water are there in 2 moles of water? Which is it? All right, 36, because every mole of water weighs 18, so if you have 2 of them, it's twice as much, 36 grams, okay? So that takes us to a term that comes up quite a bit in the physical sciences, especially chemistry. That's molarity. Molarity is a unit of concentration expressed in moles solute per liter of solution, okay? All right, so most oftenly referred to in the context of water, mixing things with 1 liter of water. Okay, so molarity is moles of solute. All right, that's the thing you're mixing in, usually into water, and liters of solution is the total of the water and what you mixed into it. Okay, so on the other hand, one way you can express solutions and concentration, okay, is ppm. And this comes up for things that are in very small quantities, and you see it a lot for things that are mixed with air. And it is a unit of concentration expressed in milligrams solute in liters of solution, okay? So 1 ppm is 1 part solute to 1 million parts solution, which then takes me to what ppm stands for, which is parts per million. So you can see then, if it's 1 part per million parts, that's where the name comes from. And that is equivalent, due to basically the density of water, of 1 milligram to 1 liter. Okay, it works out exactly to be 1 milligram per 1 liter. Again, assuming a density of water, and it can be adjusted accordingly, but for our purposes, certainly in this class, you can say that those are equivalent ratios, that 1 part per million or 1 milligram per liter. Okay, so then solubility is the ability of a solute to dissolve in a solvent. And we know that there's limitations, because you can reach saturation where there is no more that can dissolve. Okay? So then solubility is said of a solute that it has appreciable solubility. Okay? So looking at things here, solubility of grams of solute in 100 milliliters of water, no surprise, because so often that's what's assumed here. We can think about how many grams of different substances, right? We have here some sort of salt, right? We've got different, we have another type of salt, all right? So basically, in this one, this is potassium chloride. So basically all things that would fall into that, the broad category of salt, even though all of them wouldn't be, digestible salt, all right? And this with lithium chloride, but we can see that they have different amounts of solubility. How much can dissolve, okay, before we reach saturation, okay? And we see that saturation is reached at this point, over here at low temperatures around 0 Celsius, right? Not absolute zero, just 0 Celsius. There's quite a bit less that can actually dissolve. You can only dissolve about 80 grams of this sodium nitrogen oxide, sodium nitrogen oxide, let's say, all right? And then on the other hand, when you heat it up and you have, nearly boiling water over here, well, then you can have about twice as much that will dissolve. So there's always a trend that temperature allows for more to dissolve. Although if you do look at the sodium chloride, it basically is a flat line. So it's kind of the exception, although arguably there's a bit of a curve over here. But in general, as temperature goes up, more of a substance can dissolve in some quantity of water, in these particular units in 100 milliliters of water. Okay? All right. There's also the idea of precipitate. I talked about this when you put in too much sugar in the water and you reach the saturation point and go beyond it, and then it starts to build up at the bottom, all right? Well, that's the solute that comes out of the solution. It just comes right out of it because it's saturated, it can't dissolve anymore. So if you have a saturated solution, in this case, a saturated solution because 165 grams of this particular salt in 100 milliliters of water has been reached. And that's at that temperature of 100 degrees Celsius, so nearly boiling water. And by the way, that's consistent with the graph. Well, then if you continue to add more, all right, then you're going to get, or in fact, in this case, you're not continuing to add more. We're actually going to do a different trick. We're going to cool it. Because if you cool it, well, then the water now can contain less because that temperature dependence of how much can dissolve then it will decrease, all right? So if we cool the water to room temperature, about 20 degrees Celsius, well, now the water, again, based on the graph, this real data, can only hold about 87 grams of the salt. Therefore, we're going to have about 78 grams that precipitate out, right? Just falls out of the water. And where does it fall out? Well, since it's denser in the water, it falls out to the bottom. If it was less dense, I suppose it would just float up out of the water, okay? All right. So the amount of oxygen, O2, dissolved in the waters of the Arctic Ocean is greater, about equal to or less than the amount of oxygen dissolved in warm tropical waters. So which is it? Think about the temperature dependence as a general rule. All right? Greater than, all right? Because the solubility of oxygen in water actually decreases with increasing temperature. It was a trick question, okay? Most things increase. I even said that, although there was the flat line for the sodium chloride, right? But oddly, oxygen in H2O, so O2 and H2O, actually goes down as temperature goes up. Not sure the chemical reason for that or the physical reason for it, but it's a well-known phenomenon, and it leads to dramatic effects about colder water supporting more life, which is really counterintuitive, but biologists are well aware of it, and it certainly is the reality. But again, there's a temperature dependence, just not the typical one, between these particular molecules, O2 and H2O. Okay, but definitely a trick question. So by mass, water is 88.88% oxygen. So why can't we breathe water? What is the elemental formula for the oxygen we breathe and the chemical formula for water? Yeah, all right. So I'll let you think about it. All right, now on to our kind of journey here through a few topics or applications of mixtures. All right, we saw this back in the table of contents, and we're going to start this with soaps and detergents, and then we'll move into desalinating water and cleaning wastewater and other interesting topics. But let's start with soaps and detergents. So soaps and detergents have both polar and non-polar properties. Okay, and again, please review in the previous chapter polar versus non-polar. It's very important for understanding molecular bonds. Okay, so non-polar parts attract to the grime. okay? Polar parts attract to water, okay? So what does that mean? Well, the grime is the thing that the soap detergent is meant to get out, right? That's the point, all right? That's the application of it. So if we look then, what does that mean? Well, that means that the soaps and detergents surround the grime. Since one end is attracted to the grime and the molecules that are sticking out of it, and the other end is attracted to the water, well, then you have this natural ability of the soaps and detergents, which collectively play the same role, of surrounding the grime. See? Because of their non-polar ends and their polar ends, okay? And here, let's clearly show that. Here is the polar end of the soap, and there's the non-polar end, okay? Because the detergent is this long thing here, all right? Okay, all right? Because I think a minute ago I was unclear and referred to this as things sticking out of the grime, but in fact these long molecules here are the soaps, the soap and detergent molecules, okay, with their non-polar end and their polar end. Okay, good. So soap attracts grime by which type of molecular interaction? All right, and again, this is very much a review question from the previous lecture, previous chapter, because you have to think it's a non-polar end. If it's a non-polar end, what type of attraction would it be? Okay, all right. It can't be dipole-dipole because dipole requires a polarized molecule. All right, so we can definitely cross that one out. So which one do you think it is? Induced dipole-induced dipole, dipole-induced dipole, or hydrogen bonding? It's the induced dipole, because we got a non-polar end, in other words, a neutral end of the molecule over here, neutral, all right? The grime itself is neutral as well, all right? There's no electrons more on one side than the other, all right? But when those two non-polarized ends come together, they have a momentary induction of an induced dipole, which then induces another dipole. And that does hold them together. It's a very weak interaction. So certainly the detergent is holding onto the grime weaker than it is essentially attracted to the water, but it serves its purpose because it surrounded the grime and separated it from everything else. Okay? All right. So continuing with applications, now we're going to talk about softening hard water. Okay? So hard water has a high concentration of calcium, okay, and magnesium. So let's consider it. These are the molecules, the elements in this case, because they're more elemental than molecular. But these are the elements that lead to what's known as hard water. And hard water has lots of negative effects, right? Undesirable effects, clogging pipes, lowering cleaning actions of soaps and detergents. Okay, because essentially the soaps and detergents are going to be bonding to those calcium and magnesium, and then miss out on grime. You need more soap and detergent. Okay. It creates coating on things, soap scum over time. Okay, so detergent additives attract the calcium ion and the magnesium ion in hard water. Now, why is the calcium and magnesium necessarily ionized? Well, it just has to do with its ability to be easily ionized. And I suppose that's a saving grace of hard water, is that we're dealing with ions because ions have inherently some good properties that allow us to work with them. Okay, so it's a workable problem because since the calcium and magnesium is so easily ionized, which in this case it so easily can lose electrons and have a net positive charge, well, then we're going to end up with an attraction that we can deal with, okay? A actual attraction between, well, charges, the Coulomb force, going way back to our physics chapters, okay? So if we consider our positively charged sodium, all right, over here, or we can consider some positively charged calcium or some positively charged magnesium, then we can see that in these different cases, the positive charges are going to get attracted to the negative end of our polarized H2O molecule, because the H2O molecule always has a negative end and a positive end. Okay, so in both cases, we have attraction. Okay, but then what happens when the calcium and magnesium is around? Well, now the calcium and magnesium is going to be more strongly attracted to the water because it has a net 2 positive charge, both of them do, as composed to just the sodium. Okay, so that means that the sodium and the magnesium will get attracted into the water molecule. Right, it will bond with the water molecule. Okay, So some homes then contain water softening units. What do you think they're going to use? They're going to use sodium, okay, to deal with the calcium and the magnesium. Let's see how, all right? So consider the calcium magnesium naturally occurring, right, but with those undesirable effects, all right? And then let's consider putting in the sodium, okay? Well, in this case, what's happened? Because it looks like the softened water has eliminated the calcium and the magnesium and essentially replaced it with the sodium. Well, how is that? All right. Well, it's due to this ion exchange. Okay. So essentially, what's happened is the sodium bringing into the picture has allowed the calcium and magnesium to bond to all of these negative charges and has freed up the sodium. All right. So there is these basically chunks of negative charge that have pulled the sodium and magnesium out of the way because again they're stronger with their net 2 charge and thus displace the sodium. The sodium being displaced was happy to bond with the water, sort of completing the task. Okay? So the first step, oh, let's move on, excuse me. So that's the picture of dealing with softening hard water, an ionic process of giving a weaker ion and allowing it to get pushed out of the way by the undesirable stronger ion, thus leaving the undesirable stronger ion bound to these negative charges, okay, in the water softener, in the resin beads, right, negatively charged resin beads. So you need somewhere for the calcium and the magnesium to go, and you need the sodium because you need that to basically replace the ion, right? Because if you didn't have the replacement ion, the process just wouldn't be strong enough. You can't just have the negative charge there on its own, okay? Because the water would bond to it, for example. All right, so the first step to purify water, as we move on to our next topic, purifying water, is removing particles and bacteria. Well, how do we do that? Okay, well, let's consider water with impurities, all right? Well, if we allow it to have a slacked lime and aluminum sulfate added to that, then the water will react to form gelatinous aluminum hydroxide. Okay? Then the impurities are captured by the aluminum hydroxide as it settles. In the same way that the resin beads in our water purifier captures the sodium and magnesium. So you see that kind of similar idea. Okay? Then the gelatinous basically chunks here will sink to the bottom of the basin, leaving purified water above, right? So in this case, we're having this heterogeneous mixture now, and we have desirable purified water above that we can then sort of scoop off or allow to run off, leaving the sunk chunks of impurities down at the bottom, right? So we essentially just grab onto the impurities and then allow them to sink out or filter them out somehow, all right? The water is then aerated to improve the taste and smell. Lastly, the water is disinfected with chlorine gas or ozone, okay? To kill anything that's left because of health concerns. So, which of the following is not a method of disinfecting drinking water? Chlorine gas, boiling, aeration, or iodine tablets? All right, aeration. Aeration just improves the taste, okay? Has nothing to do with the actual purifying process. Iodine tablets, we didn't mention them, but maybe you've heard. They do work for killing basically everything they come in contact with, and boiling also can be effective, okay, if it's done long enough. So seawater can also be purified into drinking water, and it's a different process that doesn't involve things settling out, but instead involves evaporation, okay? So it involves distillation and reverse osmosis, okay, as alternative methods. All right, so distillation is a very straightforward method where heat comes in, allows for evaporation. Well, what evaporates is pure H2O. The salt doesn't evaporate. So then the water then builds up on the glass. It's going to condense on the glass. Okay, it's going to go the opposite phase change. Instead of changing from liquid to gas, it's going to change back to a liquid. It will then run down the gas as it's condensed. It's essentially a distillation process. And then the fresh water then will pour into some little trough, maybe run down a tube, as shown in this case here, and then fill up a jar with drinking water that you can refrigerate and enjoy later on. All right, so it's a great at-home way. Maybe if you live on a beach, like maybe this home here is on maybe near a beach somewhere, and then they can just, get their own drinking water. Okay. On the other hand, you can use reverse osmosis to get drinking water. And how does that work? Okay. Well, the picture is like this in terms of having some sort of small openings. Okay. What's important about these small openings and this definition of being a semi-permeable membrane is that the openings are such a size that they allow some molecules through, but not others. That's the general definition of a semi-permeable membrane. And these happen naturally. Biology has evolved to figure out semi-permeable membranes. We see them in living organisms, and certainly they can be manufactured by humans as well. Here, we have a semi-permeable membrane that doesn't allow these larger salt molecules to fit through, but easily allows the smaller H2O molecules to fit through. Okay, so it's permeable to H2O, but not to salt. Okay. So that then allows for this situation to be created. It starts with something called osmosis. Osmosis means that because the salt water has less H2O molecules, that the H2O molecules will continue to flow across the semi-impermeable membrane until there's an equal number of H2 molecules on both sides. Okay? Now, why would there be less H2 molecules on the side of the salt water? Well, because it's a mixture of salt and water, which means that some of the space had to be given up to salt. The fresh water is just water. Okay? So if you pour in nearly equal amounts, they're not quite equal, right? But nearly equal amounts of salt water and fresh water, the fresh water will cause H2 molecules to pass through the membrane into the salt water. Okay, what's very interesting, and again, they're going to because they have to reach equilibrium in terms of the number of H2 molecules. Because H2 molecules are pushing off of each other, they're never going to remain in a situation where there's more of them on one side if they can freely pass through a membrane to the other side. Now, again, if this membrane was fully permeable to the salt, well, then the whole mixture would just become less salty water. But it's not. It's only permeable to the H2O. So the H2O will flow until there's equal amounts on both sides. Okay. But what's so interesting about that is that means that as it flows, you get more volume of liquid on the salty side. It has become less salty, yes, right? Because it's now there's an equal number of H2O molecules, but it's actually increased in volume. And it's which allows it to get pushed up against gravity. As it gets pushed up against gravity, that creates osmotic pressure, which is just pressure, but it's called osmotic pressure because it was created due to the semi-permeable membrane. And the flow through that semi-permeable membrane is known as osmosis. Okay, so anytime you're flowing towards equilibrium of some molecule that's allowed to pass through the membrane. Okay, that's why it's called equilibrium here. What's so interesting though is it's not equilibrium in terms of a force sense. Certainly not. There's more force pushing this way. Okay, but it can't push through the membrane. Okay, but what's great is now we can apply an external pressure and push it back through. Now that's reverse osmosis. We're taking the water that freely flowed in order to have an equal number of H2O on both sides, okay, because here at equilibrium, there's an equal number, but now we're pushing that water out of the salty water. Because again, it's permeable, so since we can now apply a pressure, right, a pressure that's going to be easy to apply because already gravity wants to push it down. So we just work with gravity to apply an external pressure, and we push those H2 molecules back through. And then at that moment, we just close off the membrane completely, and we have more fresh water than we started with. Okay? That's the idea of getting fresh water from salt water through reverse osmosis, or specifically through osmosis followed by reverse osmosis. Okay? All right. So last, let's talk about wastewater treatment. We talked about it a bit, the idea of settling water out, but we're just going to return to it. All right, so screening removes the large insoluble items. The primary treatment allows the smaller insolubles to settle to the bottom or rise to the top for removal, right? And there's different, we saw the settling to the bottom with a particular case that involved aluminum molecules, all right, or an aluminum compound. But there are other types that have been discovered by chemists and companies throughout the years. Secondary treatment, however, aerates the water and allows finer particles to settle for removal. And finally, the tertiary, which just means the third or final treatment, filters the water. So here we see an insoluble water screen just catching big chunks. We see a chamber where solid grit is settling out. Then we finally have a full settling basin that would have that chemical process, so something to bond to impurities and then sink to the bottom as sludge, which is then pumped away in some sort of system, right? And then cleaner water running off. And here we have that addition of chlorine gas coming from some big tank that finally has our fully treated water. All right, that fully treated water is then going to go into an aeration tank where air is blown into it. All right, then it's going to get basically reprocessed again, all right? And then it's going to get chlorinated, all right? So there we go. We hopefully had some interesting applications of mixtures and some just variety, sort of a catch-all of chemical processes. This is hopefully a fun chapter. The next two chapters are going to be a single lecture, and they're going to be all about really kind of the chemist's approach to understanding the energy flows in chemical bonds and chemical reactions. Because you might think of chemical reactions leading to explosions. Well, that's something we're going to be talking about. Okay, so again, thank you so much for watching. I hope it has been interesting.